Welcome back to elementary statistics. In this video, I want to look at some statistics for proportions. You've studied proportions in previous mathematics courses. You may remember a proportion equation is something that looks like A over B is equal to C over D, and you can solve from there. The basic idea of proportions that you studied here is the same thing that I want to look at in this lesson, but I want to approach it from a different perspective. In previous courses, when you've seen this idea of proportions before, it has been a problem-solving tool where step one was either to recognize that a situation is one that is always something that can be discussed in proportion, or to be told directly that you're dealing with quantities that are in proportion. In this lesson, I want to take a step back from that, and I want to analyze how do we know that a certain situation is in proportion? How confident are we that the calculation you get from doing something like this actually represents the situation as it occurs in the real world? Right. So keep all of the ideas that come with that equation in mind as we're looking at this, but this equation itself is not going to be useful to us in what we're doing with proportions here. The theory of proportions starts with the binomial experiment. A binomial experiment is any experiment where the outcome of each trial has two possibilities. And for our purposes in this lesson, we're going to refer to those possibilities as success or failure, although in general, these possibilities can be pretty well anything. When we talk about a binomial experiment, the most common example given is flipping a coin. Each time you flip a coin, the outcome is either heads or tails. There are two possibilities, right? Another possibility, another thing that comes up very frequently is a yes or no survey. If your experiment involves going out and asking a number of people questions and just tallying how many people answered the question yes versus how many people answered the question no, that is very clearly a binomial experiment. But that is far from being the only thing that can happen. Imagine a board game where at the start of each turn, you roll two six-sided dice and add the results together. And then what happens on your turn is dictated or at least strongly influenced by the result on those dice. It turns out that you are in a position where if you roll a 9 or higher, you will win the game on your next turn. So when you roll two six-sided dice, there are 11 possible outcomes. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12. Right? A 1 is not possible because the lowest result is 1 on each of the dice, and 1 plus 1 is 2. But we have, based on the situation at hand, simplified this result. If you roll a 9 or higher, a 9, 10, 11, or 12, all of these together are the result of success. And then everything else, let's try a slightly thinner line so I can actually fit it in here, is the result called failure. So we can group several outcomes that we might want to look closer at in other circumstances and name them as success or failure without having the two results be the only two possibilities. Right? So it's literally two possibilities, it's figuratively two possibilities. Either way is perfectly fine. Right? As another example, I'm not going to write this one down because I don't think writing it down will make it make any more sense. Imagine that you are working for a boutique at a shopping mall, and the owners of the boutique want to know what portion, what proportion, what percentage of shoppers at the mall are going to go to that boutique or are going to the mall planning to go to that boutique. And so you position yourself near the front door, and as shoppers come in, you ask them if they will participate in a survey and ask them to name which stores they are planning on visiting in that trip to the mall. They could list any of the stores, they could list one, they could list 20, it doesn't matter. All you're going to record is, did they name the boutique that you were sent out to survey about? If they did, fantastic. If they didn't, then that's a no, and you can tabulate your proportion from there. And maybe you have some follow-up questions. Maybe it's a more involved survey, but that gives you just another possibility of where a binomial experiment can show up. For the mathematics of a binomial experiment, we are going to make a couple assumptions. We are going to assume that each trial is independent. Every time you do something in this experiment, it is the exact same situation as what you did the last time you did something in the experiment. So, for example, if your experiment is drawing um, numbers out of a pot like a lottery machine, then when you draw the number, you look at the number, you put it back in the pot before you draw the next number. So you can draw the same number over and over again. The other assumption we have to make is that the probability of success and failure are fixed values. The probability of a successful result is going to be the same in every trial. If the probability is going to change, right, trials being independent goes a long way to making sure that doesn't happen, but it's not a guarantee with just that statement. If the probabilities are going to change over the course of the experiment, then all of the math that we're doing here is going to break down. But if we have these two conditions, then we have something we can work with. I also want to mention here quickly, right, there are only two possibilities, success or failure. And the total probability of something happening is 100% or 1. So if you take the probability of success and subtract it from 1, you must get the probability of failure because there's nothing else that could possibly happen. The last thing that I'm going to assume is that we are going to pick the number of trials before starting the experiment. Going back to the experiment of surveying people entering the mall that I was talking about before. This last assumption tells us that we have to go out there and decide we are going to survey 50 people. And we're going to work until we get 50 people who give us a response, whether the response includes what we're looking for or not. Consider a very subtly different plan where I decide I'm going to go and I'm going to survey until I get 10 people who tell me that they are going to go to the boutique that I'm surveying about. Because my end condition is based on the number of successes rather than the number of trials, that will break the mathematics that we're doing. It is a subtle distinction, but it is going to be an important one. I'm not going to get into the how and why it is important in this course, just because there's not really enough time to deal with that. But we do have to work with that assumption that it is the number of trials, the number of people we survey, the number of times we flip the coin, the number of times we roll the dice, whatever it is, the number of times we do it is the determining factor of when the experiment ends, and not the number of times that somebody says yes or the number of times that somebody says no. We also want to not limit ourselves to the number of hours in the day, right? If we go and we're surveying people at the mall and we decide we're going to survey as many people as will respond between 11 o'clock and 12 o'clock, that will subtly change the math. Probably not enough to really make anything go wrong that we're talking about here, but it is technically a different thing. So again, pick the number of trials, the number of times that you are going to collect data before you start, so that the math ends up treating your experiment fairly. And again, just some notation here. We're going to call the number of successes that we get in this experiment, the number of trials that give us the success result, is going to be X. The number of trials that we complete is going to be N. And then there must be, because the only options are success or failure, if there are X successes, the remaining N minus X are all failures. For treating this experiment statistically, it turns out that the expected number of successes, which we can calculate, right, that'll be the population mean, is the number of trials times the probability of success. And that should make sense. The probability of success tells you the number or the frequency with which a success will happen. And the counting rule tells us that if we multiply the probability of success on each of the trials, that will give us the total amount of trials that are success. It's a little bit weird here because the probability is probably a fractional, well, is certainly a fractional value. When you multiply by the number of trials, chances are very good that you're going to get a fractional value there as well. And we know that it's never going to be a fractional value. It's always going to be a whole number because you're counting things. So it has to be a counting number that comes out. We're not going to worry too much about that. We'll just round as appropriate and get whole number values as our report. But that fact, that weird distinction, is the reason that I have to say that the expected number of successes is approximately normally distributed. There is a more precise distribution, which is called the binomial distribution for a binomial experiment, which takes the normal distribution and insists that all of the results that come out are whole number values. Again, I'm just not going to worry about that. There's a lot of detail that we can go into with how that works, but it affects almost nothing. So let's just not worry about it. It's approximately normally distributed. And if it's normally distributed, then the standard deviation is useful. The standard deviation of a binomial experiment is the square root of n times p times q. The number of trials multiplied by the probability of success in each trial multiplied by the probability of failure in each trial. So as an example, the one that I talked about at the beginning of this video on rolling dice. You are playing a board game and you will win if you roll a 9 or higher. And the question that I want to answer is, what is the expected number of successes, the expected number of times that you win this game if you try 20 times? And then what is the standard deviation of that rate of success? So remember, I didn't write it back out, but the idea here is that you are rolling two six-sided dice. And we've worked with the experiment of rolling two six-sided dice several times in the past. We know that the distribution of possible results looks something like this. There are 36 possible outcomes. And right here on this zigzag line is the separation between success outcomes and fail outcomes. And if you count this space in the bottom, you will see that 10 of the 36 possibilities lead to success. And then the rest, which amount to the remaining 26 out of the 36 possibilities, gives the probability of failure. And so using the formulas that I just wrote down, the expected number of successes, well, I guess I should give these labels. Probability of failure is Q, probability of success is P, and we said that there were n equals 20 trials. And so the probability of success, or the expected value, the expected number of success, is the number of trials times the probability of success, 10 over 36. Right, I could leave that as 200 over 36. Because the top and bottom are divisible by 4, so I guess I could rewrite this as 50 over 9 if that is something that you prefer. Or we could write it as a decimal number, 5.56. But again, there is no way to get a fractional number of successes. There are 20 trials, and each trial is either a success or a failure, never a fraction in between. So round to the nearest whole number and call it 6 successes. Then to find the standard deviation, we want to take the square root of n, which is still 20, times p, which is 10 over 36, times q, which is 26 over 36. All right, 20 times 10 times 26 is 5,200. 36 times 36 is 1,296. This almost works out nicely. 5,200 happens to be 13 times 400. The square root of 400 is 20. And the square root of 1,296 is, of course, 36, because we got it by squaring 36. You can reduce that fraction if it makes you happy, and we can write this as a fraction, something like 5 square root of 13 over 9. I guess that's true, but let's be honest, that is never something that's actually useful. Instead, we're going to write this as a decimal, which comes out at 2.00. So if we know the probability in the first place, we can use these tools to make a good approximation of what our number of successes should be, which is in and of itself a useful result. Although generally speaking, we're going to be going in the other direction. Generally, we're going to look at a sample, we're going to count the number of successes and the number of failures, and then we're going to divide by n to get a proportion of success and a proportion of failure. Right, so I'm going to represent the proportion of success as the letter P with a caret symbol on it. And we're going to read this as P hat. It's the letter P with a little hat on it. Again, the calculation here is x divided by n, the number of successes divided by the total number of trials run. And then Q hat is going to be the number of failures, which is n minus x over n. And of course, you can split that fraction up. N over n is 1, x over n is p hat, so q hat is 1 minus p hat. P hat and q hat are going to be fractional values. They're going to look like probabilities. Sometimes you will see them referred to as the experimental probability. And as we move onward, the tool that we're going to be looking at for working with these is to use the proportion of success and the proportion of failure as a tool for estimating the population probability of success and the population probability of failure. But again, in an example, let's look at the person who was standing at the mall entrance and surveying. Let's say that this person decided at the start of the day that they had to get 40 respondents to their survey. And so they stood at the mall. They asked people as they were walking in whether they would take the quick survey or not. They got very few people to actually bite on it. But eventually, by the end of the day, they did get the 40 respondents that they needed. And they found that not x bar, x equals 7 of them were planning on visiting the boutique in question. Then the proportion who are planning to visit the boutique was 7 out of 40. My calculator is very happy to tell me that 7 divided by 40 comes out at 0.175, or if you prefer, 17.5%. And then Q hat will be, well, 1 minus that. But again, I think about that as if there were 40 respondents and 7 of them were successful, 7 of them did say that they were going to visit the boutique that you were looking at, then the remaining 33 of them did not. And my calculator is very happy to tell me that 33 divided by 40 is 0.825. Or again, if you are happier with percents, this is 82.5%. And you can verify that if you add these things together, you get 100%. The idea of working with proportions is going to open up several new avenues for hypothesis testing. Quick idea of discussion before I wrap this video up. Can you think of any scenarios where testing something based on a proportion might be more useful than the tests on means that we've been talking about so far? Right. As always, thank you for joining me. I'll see you in the next video.